The mass transfer zone, or MTZ, is where active adsorption happens in a column. It's the region where the adsorbate concentration drops sharply, from high to nearly zero. As the adsorbent saturates, the MTZ moves from the inlet to the outlet. A thinner MTZ means faster mass transfer and better adsorption efficiency. Adsorption capacity depends on both the properties of activated carbon and the environmental conditions. Key carbon factors include surface area, porosity, and chemical nature like polarity or functional groups. Environmental factors such as temperature, pressure, humidity, pH, concentration, and contact time also play critical roles. To determine adsorption capacity, two key models are used. The Langmuir isotherm assumes a monolayer of adsorbate on a uniform surface. The Freundlich isotherm is an empirical model for adsorption on heterogeneous surfaces with varied affinities. The Langmuir isotherm, proposed in 1916, models monolayer adsorption on a uniform surface. It assumes each site holds only one molecule. All sites are identical. No interaction between adsorbed molecules. Adsorption and desorption are in dynamic equilibrium. The Langmuir isotherm can be expressed in linear form to calculate key adsorption parameters. In this equation, QE is the amount adsorbed per gram of adsorbent at equilibrium. Qm is the theoretical maximum adsorption capacity. Kl is the Langmuir constant reflecting the affinity between adsorbate and adsorbent. Ce is the equilibrium concentration in the solution. This is the Langmuir adsorption curve, showing the relationship between Ce and Qe. A higher Kl means stronger adsorption at lower concentrations. R square, the coefficient of determination, tells us how well the data fits the model. If R square is above 0.95, the Langmuir model is a good fit. If it's below 0.8, other models like Freundlich may be more appropriate. The Freundlich isotherm, proposed in 1906, describes multilayer adsorption on a heterogeneous surface. It assumes adsorption occurs in multiple layers. The surface has varying site energies. There's no fixed saturation point, though adsorption slows at higher concentrations. A dynamic equilibrium exists between the adsorbed phase and the solution. The Freundlich isotherm can also be expressed in linear form. In this equation, QE is the amount adsorbed per unit mass at equilibrium. Kf indicates adsorption capacity. N shows adsorption intensity. Lower values mean stronger adsorption at low concentrations. C is the equilibrium concentration of the adsorbate. This is the Freundlich adsorption curve, showing the relationship between Ce and Qe. A higher Kl means stronger adsorption at lower concentrations. R square, the coefficient of determination, tells us how well the data fits the model. If R square is above 0.95, the Langmuir model is a good fit. If it's below 0.8, other models like Freundlich may be more appropriate. The BET isotherm, developed in 1938, extends the Langmuir model to multilayer adsorption. It assumes infinite layers of adsorption can form on a homogeneous surface. No interactions between molecules in the same layer. Dynamic equilibrium exists at each layer. Adsorption occurs without condensation before saturation. Activated carbon plays a key role in drinking water treatment. It removes contaminants like chlorine, pesticides, VOCs, and heavy metals such as lead. It also improves taste and odor by removing chlorinated compounds. While it doesn't kill microbes, it reduces chemicals that support microbial growth, enhancing overall water safety. Activated carbon is widely used for VOC control. In industry, it captures VOCs from exhaust gases to meet emission standards. In municipalities, it reduces VOCs from sewage and pump stations, improving air quality. For personal protection, it's used in respirators and masks to block harmful VOC inhalation. In the food and beverage industry, activated carbon is essential for water purification, ensuring clean, safe water in production. It's also used for decolorization, especially in sugar, syrup, and juice processing to remove unwanted color and impurities. Additionally, it removes odors in products like oils, dairy, and seafood, preserving taste and aroma. Activated carbon plays vital roles in industrial manufacturing. In gold mining, it adsorbs gold from cyanide solutions via carbon in pulp and carbon in leach processes. In energy storage, it's used in supercapacitors for rapid charge and discharge. It also acts as a catalyst support in refining and petrochemical industries to improve reaction efficiency. Activated carbon is also used in air purification to remove pollutants and odors. In pharmaceuticals, it purifies raw materials and removes impurities. Environmental cleanup uses it to treat contaminated soil and water. It's applied in gas storage and medical fields for toxin adsorption and wound care. These uses show its wide importance beyond common applications. Thank you for watching. If you found this helpful, please subscribe, share, and comment. Your support is my greatest motivation.